Today in this video I'll be showing you how you can draw Lewis dot structures. For our purposes we're going to draw a Lewis dot structure for a water molecule, which is H2O. So you want to start off by calculating the number of valence electrons that we have. And what valence electrons means is that it's the number of electrons that the elements have in their outermost shell. So you can find this easily by looking at the group that the element is in. So for hydrogen, it's in group 1, and since it's in group 1, it has 1 valence electron. So we do 1 plus the number of valence electrons oxygen has. Oxygen is in group 6. If we skip over the metals, that means it has 6 valence electrons. But notice that we have 2 hydrogen elements or atoms, meaning that we have to multiply this original number 1 with 2. So we know that for every 1 hydrogen, you're going to have 1 valence electron, but if we have 2, we're going to have 2 valence electrons. So now you can do the same for the number 6. We have 1 oxygen atom, so it's going to be 6 times 1. If you calculate this, it's going to be 2 times 1, which is 2, plus 6 times 1, which is 6. That's going to be 2 plus 6, which is going to be 8. Now you can draw the Lewis structure. You want to organize the elements in an acceptable way. The general rule is that you want to put the element with the least amount of particles in the middle, but it's also based on many other factors. So since we only have 1 oxygen, I'm going to put that in the middle. I'm going to put hydrogen over here and the other hydrogen over here. So now you want to draw bonds between them. A bond is a line, and it shows that hydrogen is bonded to oxygen and oxygen is bonded to hydrogen. A bond is basically 2 electrons. So instead of drawing this line, you can also draw 2 electrons. So just keep in mind that this one line represents 2 electrons. So since this is 2 electrons and the other one is 2 electrons, it's 2 and 2, which is 4. That means by bonding, we used 4 of our electrons. So we have to subtract it from the total amount of valence electrons that we have. Then we get a final answer of 4. That means we have 4 electrons left to draw the valence electrons or the Lewis dot structure. So there are 2 rules that we need to keep in mind. We have something called the octet rule. That means every element, besides the ones that are exempt, should have 8 electrons around them. Meaning, in total, inclusive of the bonds, they should have 2. They should have 8 electrons. Hydrogen is an exemption to that. It's an exception to that. Hydrogen has something called the Duet rule, meaning it can only have 2 valence electrons. And this 2 valence electron has been already fulfilled by this bond over here. As we said earlier, the bond is 2 electrons, so hydrogen already has 2 electrons. So the only possible place we can draw these 4 valence electrons is on the oxygen, like this. So now the oxygen fulfills the octet rule, and the hydrogens are still in the Duet rule. This, of course, can influence the geometry and the shape of this molecule. However, that has to do with geometry and VSEPR, and we're not getting into that right now. Our second example is NF3. So again, you want to find the number of valence electrons that you have. Nitrogen is in group 5 if we skip over the metals, so we have 5 in parentheses times the number of nitrogen atoms that we have, which is 1. And now onto fluorine. We have 3 fluorine atoms, and fluorine is in group 7 if we skip over the metals, meaning that we have 7 valence electrons. And since we have 3 fluorines, we have to multiply it by 3. So it's going to be 5 times 1 plus 7 times 3, which is 5 plus 21, which is going to be 26. So now you can organize the elements. So you want to draw the element with the least amount of particles in the middle. Again, it's based off of many factors, but we're not getting into. So now that you have the elements placed around, you want to connect them with bonds. Again, a bond is 2 electrons. So by bonding these elements, we've used up 2, 4, 6 electrons from our valence electron count. So we have to subtract it from 26, which is our original valence electrons, the number of valence electrons that we had, and that's going to be 20. That means we have 20 electrons left to fill the Lewis dot structure. Again, it's called the octet rule. That means each element should have 8 electrons around it. And if we draw 6 electrons around fluorine, it's going to be 2, 4, 6 plus the bond. The bond still plays a factor here. We would have a total of 8 electrons. So now we've used up 6. Let's continue counting. 7, 8, 9, 10, 11, 12. And you want to stop when you're at 20. 13, 14, 15, 16, 17, 18. We're at 18 right now. And we know we have a total of 20. That means we have 2 left over. So the only place you can place this is in nitrogen. The reason being is that fluorine, all the fluorines fill the octet rule. They all have 8. And you can't put any more in them. So the only place you can put those extra 2 electrons is in nitrogen. And of course this is going to impact the geometry, but we're not getting into that right now. Our final example is C2H4. So again, you want to calculate the number of valence electrons. And we know carbon is in the fourth element, the fourth group if we skip over the metals. So it would be 4 in parentheses times the number of carbon atoms that we have, which is 2, indicated by this subscript over here. And we have to add it to the number of valence electrons that hydrogen provides. So we know that hydrogen is in group 1, so it has 1 valence electron. And we know we have 4 of them, so it's going to be times 4. So that's going to give us a total of 4 times 2 plus 1 times 4, which is going to be 8 times, which is going to be 8 plus 4, which is going to be 12. Okay, so now you want to go ahead and draw the elements. So I'm going to do it like this. And carbon and carbon. You can do it anyway as long as you have 2 hydrogens bonded to each carbon atom. So now you can go ahead and draw the bonds. This is 1 bond, 2 bonds, 3 bonds, 4 bonds, 5 bonds. A bond is representing 2 electrons. So in total we have 2, 4, 6, 8, 10. 10 electrons that we used for bonding. So if we use 10, we subtract it from our original valence electron count, we're going to have a leftover of 2 electrons. So now where do we put these 2 electrons? If you look carefully, this side for carbon has 2, 4, 6 elements bonded to it, meaning it only has 6 out of the 8 electrons that it needs. We don't need to worry about hydrogen because hydrogen has the Duet rule. And on the other side, carbon is also not following the octet rule. It only has 6 out of the 8. So if we put these 2 extra valence electrons that we have in carbon, on this carbon, this side fulfills the octet rule. The carbon on this side fulfills it because it has 2, 4, 6, 8. This side only has 6, so we still have a problem. If you put these on the other side, we still have a problem. So what you could do, however, is place these right there as another bond. So if you put them right there, it's gonna be 2 dots. And since it serves as a bond and it's 2 electrons, we can just write it as a line like this. So this is basically our Lewis dot structure for C2H4. These 2 bonds are called a double bond, and whenever you have a situation like we did, you can use that method and create a double bond. Now, if you and look on each side, the carbon on this side fulfills the octet rule. 2, 4, 6, 8. The carbon on this side fulfills the octet rule as well. 2, 4, 6, 8. Meaning that this is a valid Lewis dot structure for C2H4, and you're done.